One of the important concepts in calculus is the idea of a limit. And we looked a little bit at that when we talked about the instantaneous rate of change. We let our difference quotients shrink down, the interval shrunk down to 0, the h in the difference quotient. We let the limit go to 0, and we were actually able to find the instantaneous rate of change. So this idea of a limit is very important, and there's actually a formal definition of the limit, and your book gives the formal definition in section 2.3. Usually this is not covered in freshman calculus course, and we don't cover it at Hawkeye. And but what we do want to do is give you like an informal definition of the limit, just so you kind of understand the concept behind it. And then we're going to talk a lot about limits, when they exist, when they don't exist, how to calculate them in different situations, and some examples of some important limits. And so what I'm going to do in this video is give you the informal definition of a limit, and then we'll do a few examples to help you understand the definition. So first let me read through it, and then I'll kind of describe it here. So it says, suppose f of x is defined on an open interval about c, except possibly at c itself. So we say that f of x approaches the limit of L as x approaches c, given that no matter how close we want f of x to be to L, there is an open interval around c such that if x is inside that interval, then f of x will be as close to L as we desire it to be for all the x that are inside the interval. And then we'll write the limit of as x approaches c of f of x is equal to L. Okay, so now here's a diagram. Let me try to explain this definition here. So first of all, we're saying that the function here has to be defined on some interval. So for all the values in at least some interval containing c, it doesn't matter how big it is, except possibly at c itself. So what I've done is I put a space, a hole in my graph, and in this case we're going to say that f of x is not defined at that point. And so the idea of a function is we want to know what the behavior, the idea of a limit of a function is we want to know the behavior of the function as the x values here approach c. Okay, so as you get closer to c from either side, what's this function doing? What's the behavior of the function? Is it getting closer and closer to a particular value? And if it is, then we say that that value that it approaches, that's the limit of the function as x approaches c. So that's the idea, okay? As your x values approach c, the limit of the function is L if, as you get closer to this, as x gets closer to c, the function gets closer to whatever that L value is. So the way to understand this definition is that, so what it says is as f of x approaches the limit, or we say that f of x approaches the limit L as x approaches c, given that no matter how close we want to be to L, okay, so maybe I'll put some little limit on, or not limit, but a tolerance here. And there's actually a name when you do the formal definition that this endpoint is L minus epsilon, and this one is L plus epsilon. Okay? And in the formal definition, we would say for every epsilon there exists a delta, and we're not going to be doing that. But the idea here is I got my challenge here is I want the function to stay this close to L. Okay, I want it to be within this interval. Okay, so the function values need to stay within that. So L is a limit as x approaches c if I can find some interval here around c, and we call this c minus delta and c plus delta. That's like our delta interval. And this interval here, what it means is I can find an interval for any epsilon. I can find an interval so all the x values inside this interval here is going to give me function values that are within this interval up here. So for all these x values, okay, we get as close to L as I want. So if as I shrink this down and I want it to be more and more arbitrarily close to L, I can shrink this down so that it's arbitrarily close to, or that it's sufficiently close to C, so all the function value, or all the x values here lie within this tolerance that I want to get, okay? Now that's a very, very abstract, difficult definition, and if you go on in mathematics, you actually do learn about this definition, because it's what you use in order to prove theorems about limits. And you don't use this definition to actually find limits, okay? But you use it to prove different things about the limits. And some of the things that you end up proving using this definition are tools or rules, techniques that can help you find limits, okay? But the definition doesn't help you find the limits. So as far as a actual definition, and this is pretty close to the formal definition, I'm just using words like as close as you want to get to, and sufficiently close. I'm using those to kind of explain what the formal definition is talking like, but the formal what the formal definition is talking about. But the formal definition is explaining it very, very precisely in a way that gives you the ability to prove that something is going to be the limit. Okay. So now let's actually look at a few examples, and then we'll see kind of how we can find limits. Okay. So here is an example of a function, x squared minus 1 over x minus 1, and I want to find the limit as x approaches 1. So indeed, if I plug in 1 here, I get a 0 in the denominator. And so the function does not exist at the place I want to find the limit. Just like this here. See, there's a hole in this graph. So the function doesn't exist at C, but the limit is wanting to know the behavior near C, not what's going on at C. Okay? So I can't just plug in 1 here. Okay? And so, but what I want to do is I want to know what this function is approaching. And so some of the ways you could do this is I could use a graph here, and I could do like go 0.9, 0.99, 0.999, and then I could find what the function values are equal. Okay, and I can see what are these approaching as I'm getting closer and closer. And I could do the same on the other side. So the other side would be 1.1, 1.01, 1.001. Okay, and this is f of x. So the easiest way to evaluate this is not to plug each one into here, but to actually put it in my calculator in the graph. So I'm going to do that. X squared minus 1. Divide that by x minus 1. Okay, and then I'll do just my standard window should be good. Okay, so this is interesting because it just looks like a line, doesn't it? We're going to see why this is in a second. So what I want to do is I want to find, like if I actually evaluate this, so I'm going to hit second calc and hit value, and if I put in 1 here, and I actually evaluate it at 1, look, there's nothing there for my y. Okay? So the y is blank. So it's not defined at 1. So let me do it at 0.9, and I see I get 1.9 here. 1.9. Let me do it at 0.99. Looks like I get 1.99. And let me do it at 0.999, and I get 1.999. Okay, and then let's do it on the other side. If I put 1.1, I get 2.1. If I do it at 1.01, I get 2.01. And then if I do it at 1.001, I get 2.001. So it looks like this graph, and I'll kind of draw this graph because it looks a lot like a line, doesn't it? And it's going like right through here, and so it looks like we have this line, but at 1 there's like a hole, right? It's not defined there, but it looks like this is 1. It looks like as x gets closer, this 1 is our c, and as you're getting closer and closer to that from below, I'm approaching, it looks like I'm approaching 2, right? And from above, as I'm getting closer and closer from above, it looks like I'm also approaching 2, but I'm approaching it from above. So it seems like this limit here, my L would be equal to 2, okay? So this looks like it has a limit equal to 2. And we would be correct. I'm going to show you why that is in a second. But notice an interesting thing about this is, an interesting thing about this is there's no hole in this graph. And the reason for that is because of the way the calculator works. So this calculator has a certain window, okay, and the window here is -10 to 10, -10 to 10, and then it has a certain step. And so what it means here is it starts at -10, right, and it adds this step, and then it evaluates the function, and then it adds that step again, and it evaluates the function, and then adds that step again, and evaluates it, and then it just connects all those dots together. And what ends up happening is with this step, you are not going to actually evaluate the function at 1. And let me see if I put 1. This might do it here. There. So if my step instead, and I'll zoom in on this. And boy, it's hard to see. So if my step instead, I went up by 0.1, okay, and that actually changed my window a little bit. It looks, well, this went to 16.4. So if I go up by 0.1, it's actually going to land on 1 and evaluate it at 1. And when it does, you see a hole in the graph. See that? You can actually see the hole. And I was going to zoom in on that here. And there you can see that there actually is a hole in the graph. Okay, but you don't always see it on the calculator. You have to know how the technology works here. Okay, it's going to evaluate the function at different values of x down here and plot those points, and then it just connects the points that it evaluates. And if it doesn't evaluate it at 1, it's not going to show that hole, and you'll miss it. Okay, so now let me show you why this is equal to 2. So what I can do here, and we're going to learn more reasons why we can do this. We're going to learn some rules. But I can simplify this function here. I'm going to find the limit as x approaches 1 of this. But this is just equal to, let me do the limit as x approaches 1 of x plus 1, x minus 1, all over x minus 1. Okay? And so this is equal to the limit as x approaches 1. This ends up canceling out. And it equals, the behavior of it is equal to this. Now this graph is actually not defined at 1. This would be defined at 1, but this isn't the same as this. This is undefined at 1. But for all points except 1, it will have the same behavior as that. So this is why it graphed this line. This line is the line, that graph is actually the line y equals x plus 1. Okay, and for all points other than 1, it'll have the same behavior as that. And here I can plug in the 1. I don't have a problem with a 0 in the denominator. And when I plug in the 1, I get 2. Okay, and that's why the limit is equal to 2. So now let's look at another one. Now I got a piecewise function. This is one reason for talking about piecewise functions when you're doing calculus, because it helps you understand the limit a little better. And in this example, you can actually graph piecewise functions on your calculator. And let's see if I can do it here. Okay, I'm going to clear this. I'll do 0.5x plus 1. So that's the 1/2 x plus 1. And then I think what you do here is you actually put a division sign. It's weird, but then after this you're going to put an interval, and so I'll do something, or I'm going to put parentheses. Maybe I do x, and then I need to hit test. Where is that test? I'm going to hit math. Nope, not that. I knew it on my old one. There's a place where you can put in a less than sign. Oh, there it is. Second, math. And then I'm going to put in a less than sign. And then I'm going to put 4, and then in parentheses. And so that's weird. You put a division, and then you put this, and that's the interval over here. Okay? That's this. And then I'm going to say 1, 4, and then I'm going to put a division sign, and then in parentheses, I think I say x equal, so I'm going to hit second test, and say equal to 4. Okay, and then I'm going to say negative, then I have x minus 4 squared plus 3, and then this is for, in parentheses, x, and then second math greater than 4. And I think this should graph, I'm going to do it in a standard window, I think it should graph this function. Oh, yeah. Okay, so there you see, so up to 4 it did the line, and then here it does the part of the parabola, like that. Now let me look at something and see what I did here. Yeah, it's 1 for that. Now look, you see a hole there, but you don't see that at 4 it's equal to 1. But I think that's because of the step here. So I'm going to hit my window, and sure enough I got that weird step again. So let me do 0.1 for my step. And now we'll should see a point there. And we do. It's kind of hard to see. So let me actually zoom in a little bit. So it's going up. And boy, it's hard to see, but there's actually a little point right there. It was actually a little bit easier to see before. Let me look at my window to see if my step changed. Oh, you know what? Maybe there was. Let me put 0.01 for my step and then grab. But now it's not in the window. So let me change my window. I'm going to do 0 to 5, or we'll say 0 to 6, and then we'll do negative 5 to 5, and then we'll have this window be 0.1. And let's see if I can. There. And you could actually see it actually did put that little point in there. Okay, so it left a hole and it's evaluated here. So let me actually graph this now. We can do this by hand and make a graph of this. So what this is the line. It has, let me do 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So this has a y-intercept of 1 and a slope of 2, so I go up 1 for every 2 I go over. There it goes, up 1 for every 2 I go over. There's another one here, but it's actually a hole there, and this is this line here, right? And then at 4 here, it's actually equal to 1, so there's a dot, and then here it's going to be equal to this parabola, and this parabola is upside down, shifted over 4, and moved up 3, like this. And notice if I put 4 in here, 1/2 4 is 2, plus 1 is 3. If I put 4 in here, I get 0, plus 3 is 3. So both these graphs, as I'm approaching 4, both of the graphs are approaching 3. Okay? So what I wanted to do is find the limit as x approaches 3 of f of x, is what I wanted to find. So as you go from this direction, you're approaching 3. As you go from that direction, you're approaching 3. And so it doesn't matter what's going on at 4. Oops, this is 4. I'm sorry. I want to find the limit as x approaches 4. This is what I meant to show at the beginning. I want to find the limit as x approaches 4. So from either direction it is approaching 3. So the limit is 3. It doesn't matter what's happening at 4. So using our definition, no matter how close I want to be within 3 here, there's some interval around 4 where all the values inside that interval around 4, they're going to map in there, except at 4. And I don't know, did I say that in the definition? I might not open interval around C such that if x is inside this interval, and I should have said except possibly at C. So if you put this in your notebook, I should have had in here a parentheses, except possibly at C. Okay. And so here the limit is 3. It does exist and it's 3. And notice it doesn't matter what the value of the function is at that point. It could be some other value like it is here. Okay, so that's another example. So now what would be helpful to finish this video off is what are some examples where limits don't exist. Okay, so here is one, and it's a very simple piecewise function. Basically here at 2, right, before 2 it's equal to -1, like this is -1 and this is 1. So before 2 it's the function is equal to -1, and there's a hole here. Okay, so and then greater than or equal to 2, it's equal to +1. So you have the full circle, and then it goes like that. Okay, and so now it wants to know what is the value of or what is the limit as x approaches 2 of f of x. Well, as you see, as you approach 2 from this direction, you're approaching -1, and as you're approaching 2 from this direction, you're approaching +1. And so these are not, the graph, the function or the graph, either one, they're not approaching the same value from each direction. And so we would say that the limit does not exist. Okay? In other words, the graph has to approach the same value from both directions. Okay? And you could kind of see this because if I had to construct an interval, if there was a limit and I had to construct an interval around 2 so that all these values, except possibly at 2, all those values in there were arbitrarily close to that limit, I couldn't do it because values on this side would go way up here, values on this side would go down here. And so there's no way of constructing an interval that's around 2, no matter how small, such that all the x values in the interval are going to be arbitrarily close to the limit. There's not, in other words, there's not a limit here. Now what we're going to learn in another video here is you can define one-sided limits. And I'll just go ahead and talk about that here. I can say that the limit as x approaches 2 from the positive side, which is approaching it from this side, that this would equal 1, right? and then the limit as x approaches 2 from the negative side of f of x, that would equal -1. So there's one-sided limits as well, but a limit, an actual limit, has to approach the same value from both sides. And if it doesn't, then it's not a limit. The limit does not exist. So for the example that I just did, since both these graphs were approaching 3 from both sides, then the limit existed. But if this thing were moved up or down, okay, so that they didn't approach the same value, then we would say that the limit does not exist. Okay, so that's one example. Limit doesn't exist if the graph does not approach the same value from both sides of C. Okay, now that's not the only one, the only way that a limit doesn't exist. This is another way. Okay, now I could put in -1 here, and I would get 1 over 0 squared, which is undefined. And that doesn't necessarily mean that the limit doesn't exist, because when I did this one, when I put in 1, this is undefined, but the limit ended up existing. Okay, now this ended up existing, though, because this factor canceled out, and you could plug it in. Okay, this one doesn't have anything to cancel out, does it? So let's actually look at the graph of this. So this would be 1 divided by x plus 1 quantity squared. And then I'll do a standard window. So you get this graph that kind of goes off into infinity. Okay, it goes off into infinity at -1. So if I were to draw this graph, it looks like this. Here at -1, you have this horizontal or this vertical asymptote, because it's a vertical asymptote because you get a 0 in the denominator, and then it's kind of approaching this and going off into infinity, and it's doing that from both sides. Okay, so but no, it does go off to infinity from both sides. But it's not approaching a single value, right? There's no limit L, no number, such that for any, no matter how close I wanted to get to L, for any interval around here, okay, all these x's wouldn't be arbitrarily close to L. In fact, for this interval, there's going to be x values that just get larger and larger. The closer you get to -1, the larger they get. So no matter how big you make your L, I can find an interval here where the x values around -1 are going to be bigger than that. Okay, so once you try to define a limit to be a finite number, I can actually create an interval where all the x values are not arbitrarily close to L. They're all larger than L. Okay, so this thing is going off into infinity, and so this does not exist. So this is another way that a limit doesn't exist, with a vertical asymptote and the function going off into infinity like that. Okay, now we are going to be interested in when the limit is infinity. So in a sense, we could say that the limit here is positive infinity. Okay, but that's not the same thing as what we're talking about when we talk about a limit. A limit is actually a value. Infinity is not a value. So we will, in a future video, talk a little bit about limits of infinity, like limits where the graph is going to infinity, or values that the graph approaches as you go to infinity. So in other words, the limit here as x goes to infinity of 1 over x plus 1 squared is actually equal to 0, right? And then the limit here as x goes to infinity, or to negative infinity, I should say, x goes to negative infinity of 1 over x plus 1 squared is also equal to 0. So as you go off to positive infinity, as you go to negative infinity, you actually approach a value. That's the same as a horizontal asymptote. And we'll look at that a little bit later. Okay? So now, one more example where a limit does not exist. Okay? This here we have sine of 1 over x. This would be a really hard one to graph by hand, but the point here is as x goes to 0, or I should say as x goes to 0, or let me just write it, we know this limit notation. The limit as x goes to 0 of 1 over x is equal to infinity. Okay, so 1 over x has this behavior. And, oops, sorry about this, let me move it up. So this is the graph of 1 over x. Y equals 1 over x. And as you go to 0 from either side, you're going off to positive infinity down to negative infinity. And what you're doing is you're putting that 1 over x inside the sine function. So as you approach 0, this thing's just going to go off into positive infinity or negative infinity, depending on what side you're on. And either way, it's just going to keep growing and growing, and this thing's going to keep oscillating up and down and up and down. Okay? So let me graph this on here, and you can kind of see. We'll zoom in and we'll see what happens. So this is sine of 1 over x. And so here's our graph. And you know what? There's some thing. Look, this thing just looks like a straight line at 0. So problem, and do you know what it is? I think the last time I used this was for the law of sines and cosines, and we were dealing with triangles, and it was in degrees, but we want to be in radians, right? And so now let me graph. Okay, so it looks kind of like it's approaching these asymptotically, and then it kind of does a little squiggle in the middle, but it's really hard to tell what that squiggle is. Okay, so notice as we go to negative infinity and infinity, 1 over x is going to 0, and so this is as you go to negative infinity to infinity, this thing is going sine. This is going to be sine of 0, which is just 0. So that's why it's approaching that axis here. So let me actually change my window. I'll do negative 2 pi to 2 pi. And then let me go from negative 1 to 1. And then let my step be, I don't know, pi over 24. That should be small enough. And now let me graph. Ooh. And then, boy, it gave me a whole lot over there. I think I didn't do 2 pi. It went to 10. So let me actually go back, and then let me do, I did, yeah, this should be positive 2 pi. There we go. And now let me graph. So it's kind of coming, and then what you see here is it's doing a squiggle, and it's kind of hard to tell, like when you get close to 0. Do you see that? It's really weird. So what I should probably do is zoom in and see where, if it's squiggling in the middle, is it kind of, as you go to 0, is it passing through 0 at a certain point? And let me zoom in here. So there it goes. And you see that it's really going up and down and up and down. And maybe I could do let me change this y min. When I zoomed in, it changed the y min. So let me go negative 1 to 1 and do the same thing. So there it comes, and then there it's doing its squiggle. But you can see it does a whole bunch of squiggling there in the middle, and as we zoom in, it's just going to get messier and messier. Let me zoom in one more time. And look, it just gets messier and messier there in the middle, right? And if you zoom in, it isn't going to get any better. So this graph here, right, is kind of like coming You know, I don't know if like from here, and then it just zooms in, and then it just goes crazy in here, and then like goes like that. And here, as you approach 0, it just oscillates more and more and more and more and more, because as you're approaching 0, your sign is going off to infinity. But it's going off to infinity as you're getting close to 0, which means this thing just oscillates forever. Okay, so any interval around 0, no matter how small, you're going to have an infinite number of oscillations between -1 and 1. So there's no way to have a limit, because you can't get an interval around 0 where all the x values are going to lie arbitrarily close to whatever you want the limit to be. Okay? And that's the idea. So 3 ways that limits cannot exist would be if they're not approaching the same value from either side, if they're going off into infinity, you can say exploding or whatever, off into infinity, or if they're just oscillating forever as you approach the value. Okay? So those are 3 common ways that limits do not exist. But a lot of limits do exist, so in the next several videos we are going to learn some of the rules that you can use to calculate limits. And some of these we kind of already took advantage of as we talked about, like as we talked about this one, being able to factor it and cancel and take the limit of this, and to know that that limit would be the same as that. I'm really, in a sense, taking advantage of some of the rules that we're going to look at. So these rules are just going to make concrete things that we've already done. Also, when we found the instantaneous rate of change by making h go to 0, and we said, oh, if h goes to 0, we can just get rid of it because we substitute 0 in for h. All of that's taking advantage of the rules that we're going to learn in the next video. So we'll learn those rules, we'll look at a bunch of examples of how to do limits, and then there's a few more other topics that we'll talk about.